Hey, what up, y'all? How's it going? Oh, forgot my little slide was on. Hey there. Hi, everybody. Let me go ahead and get started today with the two parts of the warm-up. Though, like always, I'll give people a few minutes to shuffle in, so I'll take a minute to start. While everybody's signing in, I don't know about y'all, but have you guys settled into like a summer type mode yet, like a funk or whatever? Like getting up late, playing extra video games, watching extra TV, you know what I'm saying? Like with the year winding down. Wait, is my mic on? Can you guys hear me?
Yeah.
Oh, okay. I'll be real with you. Ever since I graduated, because I'm done with class, I've already kind of started to settle into like a summer type mode or whatever. And almost every summer I play a bunch of Minecraft. I've been playing too much Minecraft with my friend Steven. We like have a pretty nice setup going. We're already at the point where we're like making farms, and we got a potion stand going and an enchanting table. So we're making better equipment. I think we might try and finish the game today. Have any of y'all ever played adventure mode all the way to the final boss?
Wait, adventure mode?
I'm sorry, survival mode?
Survival. Yeah.
No, we did.
Oh, yeah?
We did, yeah.
That's awesome. Yeah, I try to do that once a summer, and I usually try to do it over like 3 or 4 days, like take it nice and slow. But boy, is it satisfying. As everybody logs on for the next few minutes, do y'all want to see my Minecraft space real quick?
Yeah.
Just the home base? Let me see if Zoom is cool with that real quick. Oh, also, quick reminder while this main screen is being shared, today's picture day. So in the next few minutes, get yourself presentable so that we can turn on everybody's webcams to take a nice Zoom class photo for the yearbook of all things.
Are we allowed to have like a nice background? Like,
I don't want anybody's digital backgrounds on, just like whatever your background is. And then if it's the digital background, if nobody notices, that's fine. But it can't be like from a video game or whatever, like a bunch of my juniors have.
Like if it's a beach.
A little corny, but fine.
Yeah, because like
that actually might be perfect.
Wait, this is for the yearbook?
I mean, not like the official class photo or whatever, kind of.
Yeah, like a little like picture.
Yeah.
Then I'm just gonna switch to my computer so it has like a better webcam.
Yeah. That's why I'm gonna give y'all a few minutes before we take the photo to like get yourselves put together and such. And in the meantime, I don't know how this is gonna perform on Zoom, but is this like is that showing the right way?
Yeah.
Lol. Okay. It's real dumb, but we got everything like nice and organized. And then upstairs we have our like own beds with like treasure chests. And then downstairs I'm growing, I don't know if you know how the potion system works in this game, but
you need nether wart.
Yeah, you need nether wart. So, oh my God, go down the thing. So downstairs is my like nether wart farm. And then, oh, it's so slow with Zoom running at the same time. And then outside, we got a little farm, and then off in the distance is like where all the cows and sheep are.
Wait, so you've beaten the Ender Dragon?
Oh yeah, I do it every summer, but this is just my attempt at it this year. But I think we're gonna do it either today or tomorrow. We almost have enough eyes to make the portal. But yeah.
Mr. Robinson?
Yeah.
Taki was me because it was my mom's name. I forgot to change it.
Oh, that's fine. I just want to make sure it's not a senior pulling a prank or whatever.
Yeah.
Oh heck, boy, that music's loud. Okay, so first, let me go ahead and read off the warm-up for today and kind of tell you what the plan is for today. Then we'll take the class photo, and then part of that class plan is I'm going to be doing a little bit of lecturing today, just because I think this is an easier section. Maybe like understanding the proof part of it is hard, but I think the homework is pretty easy because it really limits itself to 2 kinds of questions. Today, we're going to talk about an experiment that has to do with question part 1. And then I'm going to talk a little bit about what it takes to invent pi. Like, because before in section 1, we talked about all these details about how pi evolved over time. And that final equation that I used in the bonus question on the quiz, that uses the equation that is the currently like the most accepted, best way to formulate and calculate pi. Today, I want to talk a little bit about how the ancient Greeks did it, just because with your guys' level of mathematics, I think that's about the level of proof that you'll be able to grab onto. I just want to give you a little bit of a feel for what it feels like to invent new mathematics.
Wait, is today workshop?
Today is workshop, but since it's an easier section, I'm going to lecture a little bit up top. Of course, this won't be stuff on a test or whatever. I will reserve, however, the last maybe 25 minutes of the class for workshop time in case there are questions out there on the homework. So warm-up item number 1. The altitude of Mount Baldy is 4,193 feet. The radius of the Earth is 20,902,231 feet on average. How far away can you see Mount Baldy before it disappears over the horizon? And this seems like an odd question to ask, like how does one figure that out? Turns out it is based exactly on what we discussed yesterday. This is absolutely a tangent question. And this is a general approach that you can use to determine how far away it is that you can see certain landmarks based on their height. It has everything to do with the tangents of circles. So let me give you a little bit of explanation of what I mean. Imagine you're on a road trip and you're driving towards a city, right? And maybe this is best imagined with Vegas as you approach it, or San Francisco as you approach it. For this example to work out, the city has to have, pretty tall buildings. As you drive towards a city, what can you see first on the horizon?
The peak of like the tallest building.
Right, the thing you see first from farthest away, it should be the peak of the highest building, right? That is to say that you can see the top of very tall objects over the horizon because the Earth is curving towards them and the object is off in the distance. So you can actually literally calculate how far away objects are visible from on a planet with their height and the radius of that planet itself. So let me give you guys a little bit of motivation for this question. Okay. I'm going to go ahead and say that this right here is the Earth in profile. And to make any of the important features visible at all, I'm going to have to exaggerate the height of the objects that I draw on here. That is to say that if you were actually looking at the Earth from outer space, objects on it are so short that the Earth appears to be perfectly smooth. Even the tallest thing in the world, and what's the tallest thing in the world? Which mountain?
Mount Everest?
Yeah, even Mount Everest, if you look at the Earth in profile, you couldn't see it like as a bump on the surface. That's how smooth the Earth is, radius to height of objects relative-wise. So just know that this diagram I'm about to draw is a gross exaggeration, but it's just so that the effect that I'm talking about is a little bit more visible. So let's go ahead and say that this right here is going to be Mount Baldy. It's that tall somehow. And we are off this direction, right? We're somewhere on this part of the Earth's surface, some distance away. So that is to say that, well, okay, if I was over here, would I be able to see Mount Baldy?
Probably not.
Definitely not, right? Light travels in straight lines, which is to say that if there is light leaving the top of Mount Baldy, because you always observe things as just like the beams of light that are bounced off of them, we have a hard and fast rule that says light is only visible along straight lines. So we can figure out all of the places where the top of Mount Baldy could be seen from by drawing a perfectly straight line. So that is to say, from the top here to the surface, that this would be the furthest distance away that Mount Baldy would be visible. Because at this point, it would hit the horizon, right? Any light leaving the top would hit the horizon, and if you're back here, you just can't see the top of Mount Baldy. You can only see things if they're close enough to you so that they're not lost over the horizon by the curvature of the Earth. I mean, of course, Mount Baldy is visible at any of these closer positions too, right? So you could see it here, you could see it there, or whatever. But this would be the furthest possible distance at which you could see it. Guess what kind of line this is?
Tangent.
That is a tangent line. And so we can go ahead now and we can use some circle problem-solving techniques in order to figure out how long this tangent line is. I want to know what this tangent line L is. How far away can you be from Mount Baldy before you can't see it at all? And so when in doubt, when it comes to trying to solve circle problems, what's our best technique? If it seems like there's not enough information, what should we draw in?
Radius.
We should draw in some radii of the Earth because we know that they're all equal. So I'm going to go ahead and draw one radius from here to where we're standing, right? So you are here. If you are standing at the position at which Mount Baldy is just barely visible on the horizon. And I'm also going to draw in a second radius right here, another R. So this is R and this is R. I'll stop there. That should be more than enough hints and information for you to solve out this question, item number 1. And then we're going to talk a little bit about a historical fact about Mount Baldy. And then item number 2 over here on the right, this is just a vanilla perimeter question. I have a quadrilateral circumscribed about a circle, and I'm giving you some lengths. Use that puzzle technique that we used yesterday to solve out for the missing lengths, and then calculate the perimeter. So that is to say, if you can figure out what this and this are, that will give us what the perimeter is in total. In the meantime, let's go ahead and take a class photo. So get this down. You have 10 seconds. Perfect. Okay. Let's go ahead and do this. So item number 1, Mount Baldy is 4,000 feet tall. And so how is it that we can solve for its visible horizon distance? What is the trick?
Since the tangent is meeting the radius at one point, that means based on our rule, it's forming a 90-degree angle. That means we can use the Pythagorean theorem.
That is spot on. I just wish I knew where my pen was so that I could write that down. What the heck? How can pen just disappear? Wait a minute. Oh, I am sitting on it. Okay, yeah, that is correct. So what we need to do here is we need to use the Pythagorean theorem, because if light can only travel in a straight line, and it hits this point and can't travel past it, right, based on the curvature of the Earth here, then this right there is a 90-degree angle. And so this is a right triangle where the Pythagorean theorem applies. The trick is that this length here is the radius of the Earth. This length here is our answer. What's this length? What's our hypotenusal length?
It's got to be the height plus the radius.
Yeah.
It's got to be the height of the object that we're discussing plus the radius. So if you do this treatment with the Pythagorean theorem, you can do this for the height of literally any object on Earth, and it'll tell you how far away that object should be visible from on the horizon. Nonetheless, let's go ahead and set this up. So this is to say that I'll do it the nice way. This is to say that r plus h, the radius of the Earth plus the height of the object squared, should be equal to L squared plus the radius of the Earth squared. Is this okay? So this is just the Pythagorean theorem? Yeah?
Yeah.
And so let's go ahead and solve this for L squared. How do I get L squared alone?
Minus r squared. Or
Yeah, we'll subtract r squared over to the other side. So this is going to be equal to r plus h quantity squared minus r squared. And I want to actually simplify the right-hand side just so that it's easier to plug in the terms when we solve for L. What is r plus h quantity squared? What's the rule with squaring a binomial?
It's r squared plus 2rh plus h squared.
correct. And keep in mind out there, that's because this is r times h, sorry, r plus h times r plus h. And when you multiply two things, you have to FOIL them. If you FOIL this with itself, that's where our middle term comes from. And so what cancels on the right-hand side here? Why bother expanding that?
You do minus r squared. You like
What's
You
r
cancel.
squared minus r squared?
0.
0.
Anything minus itself is 0. And that makes it so that we don't have to deal with the radius of the Earth squared. Because I think for most of your calculators, if you took 20 million and you squared it, it would probably overflow your calculator. And so now I can take the square root of both sides. And so the visible distance for an object on Earth, that L, should be equal to the square root of 2RH plus h squared. So L in this case will be equal to the square root of 2 times the radius of the Earth, which is a little bit more than 2 million. Actually, almost 20, sorry, a little bit more than 20 million. 20, 902, 231. Then multiplied by the height of the object itself, in this case, the height of Mount Baldy, 4,193 feet, plus the quantity of the height of Mount Baldy, 4,193 feet, quantity squared. So I'm going to go ahead and punch all this through my calculator and see what we get. And then to get a good feel for what this answer is talking about, we'll also go to Google and convert it to miles. So this is to say 2 times 20 million, 209022231 times 4193 plus 4193 squared. And then I'll take the square root of that. So on Earth, Mount Baldy should be visible from about 400,000 feet away. So if we go to Google and ask Google what that is in terms of miles, here we go. That is to say that at this, with that height of the mountain, if you're at sea level, you should be able to see the very peak of Mount Baldy from at most 80 miles away. Or the other way to think about it is that if you can see Mount Baldy at all, you are less than 80 miles away. Is this okay?
Yeah.
That is my favorite use of tangents. Hands down, that is my favorite use of the logic about tangents. How far away can you see objects on the horizon? Oddly enough, it's just the Pythagorean Theorem using the radius of the Earth. Anyway, yeah, so this answer, 418,692 feet, which breaks down to about 80 miles. Good stuff. Item, yes.
For the rest of the year, we're just going to keep learning things like this just for our own knowledge.
That is, you know, believe it or not, that is the only actual reason why you learn anything ever. Yeah. The grades matter a lot now that you're in school, but in the grand scheme of things, the stuff that you learn for your own benefit and interest are the only things that you'll hold on to in the long term anyway. Item number 2, perimeter. So what's the deal here? What's the other fun feature about tangents that isn't just the 90-degree part? What other rule does it give us that's applicable here?
I know what it is, I just can't say it. Let me look at my notes.
So
Yes?
the point, basically the tangent or the part that touches the edge of the circle to the other part that touches the other end of the circle, like edge of the circle, they're congruent.
So right here, this would be the point of contact.
Yeah, until the intersection point.
Point of contact. And then this right here is the point of?
Intersection.
So this is the point of intersection. So the distance from the point of contact to the point of intersection on each side is?
Congruent.
Congruent. That's the magic word. And so this is congruent to that. This is congruent to that. This is congruent to that. And this is congruent to that. And so there's actually enough information here for us to find all of these missing lengths. So how do we go about doing that?
Well,
And from here forward, I'm going to use a different colored pen just to show the difference between what numbers we started with and what numbers we were able to obtain.
Oh, okay. So in the left top corner, like the top corner, the other one is 7, the congruent one,
Yes.
and that would make the other side 11 because 18 minus 7.
Yes, and how is that useful?
Because then we find out the next one is 11 too.
Wonderful. Mhm.
And then you can 11 plus 20, wait, 31. Okay. So since that's 20, it means that the angle next to it is also 20. And that means 28 minus 20 would mean that that last one is 8.
And again, how is that last part useful?
Because it means that that last angle that last line we don't have is also 8.
Wonderful. So because all of these subsegments on the outside are congruent, we can use subtraction and comparative values to find the missing numbers. So if I know that this and that are both 7, but this total is 18, 7 and 7 means this gap must be 11, which gives us the missing gap. Very similar logic rotates all the way over here to show us that this is 8. However, keep in mind that that's necessary but insufficient to get the answer. We still need the total perimeter. So that'll be, and I'm going to start from here and go around, 8 plus 7 plus 18 plus 11 plus 20 plus 28. And that is to say that our total perimeter for this quadrilateral is equal to 92 units, whatever these units may be. Is that okay for these first 2 questions in the warm-up, the do now, the altitude of Mount Baldy and the perimeter of a quadrilateral?
Yeah.
Cool. Okay. So here's the additional side lesson I'm going to do today before we use the last 30-ish, 25-ish minutes of class to do notes. The reason why I use Mount Baldy, and by the way, this is the actual height of Mount Baldy, is the fact that we talk about the speed of light a lot in this class, just because it helps us relate geometry to the real world. Light is nifty, it travels in perfectly straight lines, and it travels at a perfectly constant speed, right? Which is why in outer space, we can use light itself to measure distance. We say that, how far away is the Earth from the sun? Earth to sun distance is how many light minutes? Anybody remember?
Oh, isn't it like 7 minutes?
Very close. It's about 8. So that is to say, light leaves the surface of the sun, it travels 8 minutes, and then it arrives at Earth. Because light travels at a constant speed, saying that the distance from the Earth to the sun is 8 light minutes means that if you take 8 minutes, multiply that by the speed of light, it will tell you exactly how far away we are from the surface of the sun. However, what I think is a fascinating question is, well, how do we know the speed of light? How does one measure the speed of light, right? And interestingly enough, the speed of light was actually measured at Mount Baldy, which is visible from campus, because campus, when it's open, is less than 80 miles from Mount Baldy. It's one of the big mountains way off in the distance over the horizon if you look out towards Arcadia. So today we're going to talk real quick about the speed of light. I just think it's wickedly interesting. So let me tell you about measuring the speed of light. So this guy is Albert Mickelson, and he's famous for an important experiment called the Mickelson Morley. Can you guys see the screen I'm sharing?
Yeah.
Yeah? Okay. And the Mickelson Morley experiment, I won't talk about it here. If your guys' physics teachers in the future are good, you'll learn about it then. But basically, the Mickelson Morley experiment proves that space is empty. It proves that outer space is a vacuum and not filled with some sort of fluid or gas or whatever. And that experiment was done before we had sent any objects to space. So it was really the first time that we knew that for sure. He actually did that experiment, the Mickelson Morley, kind of early in his career, relatively speaking. Mickelson Morley experiment, real big, in 1890. But one of the last things he did before he died in 1931 was he hiked Mount Wilson with a team of researchers, and he used Mount Wilson itself in order to measure the speed of light. And even though he did this in 1927, amazing work, even though this experiment is almost 100 years old, his answer was within 0.01% of the number that we use today. So this is really the first time we got a good number, basically the number that we use today for the speed of light. And here's how this is done. You actually need two mountains to do this experiment. So one of them is Mount Baldy. The other one is Mount Wilson. And the actual name of Mount Baldy is Mount San Antonio, which is why you'll see Mount San Antonio also on this diagram down below. The way that this is done is that if you want to know the speed of something, you let it travel, and you measure the distance and the time, and then divide those two numbers, right? So if speed is equal to distance over time, if you can measure the distance and you can measure the time, you can divide those two digits together in order to get the speed. So starting at Mount Wilson, they send out a pulse of light, just a flashlight with a thing in front of it that causes the flashlight to blink, you know what I'm saying? And it bounces off of a mirror. That mirror sends the light to Mount San Antonio, which bounces off of another mirror. That bounces the light back to Mount Wilson. And so that gives us the distance. It's about 22 miles between the mountains. So the total round trip distance has to be about 44 miles in total. So is that okay for the determination of the distance between these, or sorry, the distance the light travels?
Yes.
So that's the first part of the experiment. And also, I think it's really weird that this really important experiment was done so close to campus. On this map, this is Pasadena. So Mount Wilson's right up above us in the mountains. And then the other mountain is kind of out above Pomona.
I kind of like live on like the foot.
Yeah, I think most people's houses are visible somewhere on this map. Even my spot is. I live somewhere in this general region that I'm not going to outline too clearly. But yeah, I mean, you know, we live in an important place historically. In a lot of contexts, a lot of good science has happened in Southern California, despite the fact that it's also mostly famous for the movie industry. Anyway, so the distance that the light travels during this experiment is 44 miles total, which is just the distance between the mountain's tops times 2, because the light has to go from mountain 1 to mountain 2, bounce off of mountain 2, and come back. So then the question becomes, how do you determine the time? And the time is determined by a very clever technique using an octagonal mirror. So how many times does this, or sorry, how many sides does this mirror have?
8.
8.
Yep, 8-sided mirror. So here's how this is used to get the time. If the mirror was perfectly stationary, right, then it will always bounce the light back perfectly into the telescope. So like I said, we're blinking a light and it is hitting the mirror, going to the other mountain, bouncing back. But when it comes back on the other side, it's going through a telescope into a scientist's eye, and they are looking for that light. So if the mirror is not moving and the mirror is perfectly lined up, then the observer will always see the light returning through the eyepiece. So the light bounces off of side 1, goes to Mount Baldy, bounces off the mirror there, hits side 3 of the mirror, and then off of side 3 of the mirror, it goes into the observer's eyeball. Are there any questions here? Okay, this is boring. This is why, in order to measure the amount of time that it takes for the light to come back, we set the mirror in motion. It is spun very quickly by a very, very fast motor. And so the reason why we spin it is that if the octagonal mirror is slightly off position, when it comes back, side 3 of the mirror will be askew, and the light won't be bounced into the observer's eye. Instead, it'll be bounced to the wrong direction, and we know that the mirrors are poorly aligned because the observer looking through the telescope will see nothing but darkness. They'll just see a black background. And so we increase the speed of the mirror, increase it, increase it, increase it, increase it, to the point that, and now notice the position of the mirror in this frame compared to the original, right? 8 is at the top, and then when it returns, it bounces off of side 3. But if it's rotating, it starts off by bouncing off of side 1. And then by the time it comes back from the other mountain, the mirror will have rotated exactly 1/8 of a rotation, so that when it comes back, it bounces off of side 2 of the mirror and then goes into the observer's eye. Is this okay? So one more time. If the mirror wasn't moving, we would always see a light when the light bounces off of the mirror and goes into the eye of the observer. We then set it in motion, and if the speed of the mirror spinning is wrong, the observer won't see anything at all. It'll be bounced the wrong way and it won't go through the telescope. But if the speed of rotation is just right, if it makes 1/8 of a rotation every single time the light returns, then it will be in motion and the observer looking through the telescope will be able to see the visible light. Well, the nice thing about this is that if this is true, if this setup is correct, then the amount of time that it takes for this thing to rotate 1/8 of a turn is the exact same amount of time that it takes for the light to travel that distance, because we're using a blinking light. So by saying that the total distance traveled is about 44 miles, that gives us delta x in that equation down below. And if our notions about the way that this rotating mirror are correct, then 1/8 of the time that it takes for this mirror to make a full rotation, that is our time interval. And dividing these two numbers will give us the velocity of light. And like I said, this experiment was so good that even though this was done almost 100 years ago, the numbers in the paper are within 1% of the accepted answer that we use today, which is determined by far more sophisticated methods. Great experiment, all analog equipment. All you need is a really, really fast mirror and some hiking sticks. Are there any questions on the speed of light measurement made at Mount Baldy?
No.
Cool. Nonetheless, the rest of this time is yours to work on the homework. If you have any questions on specific questions on the homework, just let me know which ones. I have it open in my other monitor. And of course, if you are done and it's already uploaded to Google Classroom, you can head out and have a slightly early lunch today.
Okay, see you, Mr. Robinson.
Mm-hmm. You too.
See you.
Bye, Mr. Robinson.
Bye.
Peace.
Mr. Robinson, I'm looking at like the Google Earth like picture of like Mount Wilson, and the thing is still like there where they did this like experiment from.
Yeah, there's a plaque there. If you hike to the top, there's literally a plaque that says that this conducted was experiment in this place and this day, because I can't overemphasize how important it is to physics to measure the speed of light.
Yeah, and they have like a spot where it's like scenic view from Mount Wilson.
Mm-hmm. Yeah, you can hike all the way up there, and it's so tall that this calculation that I used in the warm-up of like how far away can you see stuff on the horizon, it kind of works both ways. So normally you can only see about 20 miles flat out across the horizon, and the higher you are, the more stuff that you can see. If you're at the top of Mount Baldy, you can take this notion both ways to say that, well, the distance from here to here is 80 miles, so I can see Mount Baldy when I'm 80 miles away from it. But basically being on top of Mount Baldy gives you 80 miles horizon to horizon instead of the regular 20 miles horizon to horizon. When you're on Mount Baldy, you can see Santa Monica. Like, you can see the Santa Monica Pier from there.
Yeah.
You can even see all the way out to the Channel Islands, even though they're like a good 20 miles off the coast.
Yeah.
20 miles?
And
No, they're like 15 miles off the coast. Sorry, you were saying?
they have a plaque there that it's named after this guy named Don Benito who like first did the trail, like in 1811.
That historical information, my brain does not go back far enough for. Though that does sound correct and interesting. I only know about the Mickelson Morley history in any important detail.
Yeah.
But yeah, if you ever want to know like that same calculation for anything, I think another interesting one is like when you come into New York Harbor, you go in past the Statue of Liberty. Another common use of this example question is like the Statue of Liberty is a certain height. How far away can you see it on the ocean? Same idea.
Yeah.
Exact same equation. Oh, I'm so glad tomorrow's Friday.
Mount Baldy is only like an hour away, but it's like snow-capped sometimes.
Oh yeah, the only thing that determines whether or not something is snow-capped is its height. Because as you go upwards, the pressure on the air drops, and so it's like the phase properties of water drop. Basically, it's easier for ice to form.
Higher up.
Yeah, it's easier for ice to form higher up because the lower pressure of the air makes it so that the air temperature is lower. So for any region with a tall enough mountain, there will almost always be snow at the top.
It even has like waterfalls and rapids.
Yeah, most mountains tend to have a bunch of rivers that come out of them because like the amount of ice and snow at the top is gargantuan. It's like hard to put a number on. And as the spring and summer go on and that ice and snow melts up there, that's what feeds almost all of the rivers, even in the area that we're at. So it's a weird thing to think about, but like I live right on the LA River, and normally the water out front in the river is about 4 feet, maybe 5 feet. Every now and then when it rains, and it seems like rain constitutes a lot of water, the level of the LA River will come up to about 10 feet. But the times in which the LA River is highest is right in the spring, like this time of year when it's starting to get hot, because even though it's not raining, all of the snow in the mountains north of Burbank, and some of it you can't see because it's beyond the crest or whatever, but as that snow begins to melt, that is melting into water and flowing downhill and feeding all of the rivers in the valley. So even on a dry, hot day, you can get a sudden rush in the river water because it's melting snow melt up the mountain. It's a really important thing to keep in mind if you ever go hiking or backpacking in the backcountry, that it's not just rain that can cause a flash flood. A heat wave where there's snow can also cause a flash flood. Check the weather before you go backpacking and talk to local park rangers about changing conditions. I never use PowerPoints to teach. It's really, I think that's like the only PowerPoint I've shown y'all all year, huh?
Yeah.
We still have about 15 minutes to lunch. So again, if y'all have any questions, just holler at me. I have the homework open in my other window. But if we're all just like working at the same time and hanging out and stuff, feel free to chat if you just want to ask questions about anything. I'm gonna edit some of my YouTube videos from the other day so that I can post them to YouTube. Just gonna be doing some side work.
Page 29.
Answer is 12. Three on page 29.
Yeah, I don't
That's-
really want to know the answer. I just want to know how to do it.
Oh, I mean, the answer is how to do it. It's actually just asking for the application of an identity. You're just applying the information that two tangents that intersect on the outside of a circle are the same length.
Oh.
that is all that that setup is talking about. So those are both tangents on the outside. And if one of them is 12, the other one is also length 12, just like how if this is 7, this is 7.
Oh, okay. Yeah. Oh, and didn't you say today's like a picture day or something?
Yeah, we took it at the top of the class, like in the first 10 minutes.
Oh, I was having internet issues. I was out.
I apologize. You may have been excluded then.
It's fine.
Yeah, or if you want, you can take, like use the webcam to take like just one picture and I can Photoshop you in pretty easily.
No, it's okay.
Are you sure?
Yeah,
Okay.
I don't mind.
Yeah, I don't even think they're going to get printed that big anyway. I don't think they're getting full pages. I think they're just working on a collage of all of the times we were on Zoom. Oh my God, I'm in a tangle of wires. Man, so like most days I take my laptop downstairs to my like game room where I have my retro TV and I do a stream. Moving my laptop back and forth from here to there and all of the cable swaps and setting changes like required is starting to get annoying. But I'm not so rich that I can just be like, oh, we'll just buy another laptop and have one for each. I need to get a better system going.